All right, we're asked to rationalize the denominator for this expression. What that entails is simply getting rid of any radicals in the denominator. If you feel comfortable with rationalizing denominators when we have just one term in the denominator, you might think the move would be to multiply this by root 2, square root of 2 on top and bottom. The issue here is when we multiply this current expression with this, the property of distribution comes into play. So when I multiply this, I need to distribute these things to both the numerator and the denominator. So the result would be 8 square root of 2 plus 2. This is 2 right here because the square root of 2 times the square root of 2 is 2. In the denominator, we would get 5 square root of 2 plus 2 again, because the square root of 2 times 2. The issue here is that move didn't do anything for us. We still have this square root in the denominator, so we need a bit of a better move. All right, before we figure out what to multiply by, I want to just kind of do a little backstory to this on something you've seen before with polynomials. These are just two quick examples. So in this first example over here, I'm multiplying x plus 3 times x plus 5. And remember, this is a FOIL, or you're basically double distribution. So we're multiplying the x times the x and the x times the negative 5, getting my first two terms here. And then the 3 gets distributed through this second polynomial to give me my 3x minus 15. And then we just clean things up, and it's always just cleaning up this middle term right here. So negative 5x plus 3x gives us the 2x, or negative 2x here, down here. There's a special case of this. In this case over here on the right, I'm multiplying what we call two conjugates together. These are two binomials that are exactly the same except for the operation that splits the two terms here. So we have a x plus 5 and then an x minus 5. This ends up being what we call a special product, and it's because of what happens to the middle term. So unlike that first example I was just talking about, what I get is like this perfect canceling of these two middle terms, this minus 5x and plus 5x, and so those cancel each other or add to 0, and I'm just left with these two end terms. And what these two end terms end up being is just that first term in these conjugate pairs, so the x times x to get x squared, and then the second term is just this 25, which is the 5 times 5. And that gets generalized, and so we have this statement right here in blue. This is called the difference of squares, or the product of two conjugates. And the whole idea is when you multiply two expressions like this, you just end up with the first term squared minus the last term squared. And that squaring effect is really useful when we're dealing with radicals and trying to get rid of radicals, because any radical term or anything with a square root, when you square it, the radical or the square root is going to go away. As an example, we have this conjugate pair right here. And I won't just apply this formula up top, I'll actually do the multiplication, but you'll see this will be true. And so I'm going to distribute this 4 through the second polynomial. So I'll get 4 times 4 is 16, and 4 times negative root 3 is negative 4 root 3. And then the root 3 getting distributed through gives me a plus 4 root 3 and a minus 3. Cleaning that up, what I get is that same situation as I had up top here with these middle terms. So in that first case I was talking about, right here was this negative 5x and plus 5x that got canceled. In the case that we have down here, it's a negative 4 root 3 and a positive 4 root 3, and those will just cancel each other out. So when I finish the simplifying of this, what I'll get is 16 just minus 3, or 13. And the crazy part of this, and this is important because of what happened in multiplying these two conjugates, our final expression we get, the product of this multiplication, has no square roots in it. It's just a number. It's a real number. And that's an important feature. And the idea is that when we multiply these together, what we ended up with was just the first term squared. So there's 4 squared, or 16 here, and then minus the square root of 3 squared, which is just 3. All right, and so it applies to our original problem. What I'm going to multiply this expression by then is the conjugate of the denominator. So I'm going to multiply this by 5 minus root 2 on top and on bottom. I'm doing it on bottom in order to get this conjugate multiplication to where I'm going to end up with a real number on the bottom. Up top, it's going to be a distribution or a foiling problem. It's going to be a little bit gross, but it won't take much to clean it up. In the numerator, I'll distribute the 8 through first. So 8 times 5 is 40. 8 times negative root 2 is negative 8 root 2. And then I'll distribute this root 2 to both these terms to get plus 5 root 2 minus 2. On the bottom, I could multiply all this out, the same thing I did in the numerator, but I know how this multiplication works. It's like the previous example we were just talking about. When I FOIL these, what I'm going to end up with is just this 5 squared minus this root 2 squared, which is 25 for 5 squared, and the root 2 squared is 2. And that was the whole purpose of what I just did, was my denominator no longer has any radicals. And so we'll just clean up the numerator. Combining like terms, a 40 and the negative 2 give me a 38. And the negative 8 root 2 plus 5 root 2 is negative 3 root 2. And the denominator, I got 25 minus 2 is 23. And there is an expression equivalent to my original one, but there are no radicals now in the denominator.